Welcome back, Regents students. Today we will be extending what we learned yesterday. Yesterday we learned the law of reflection, and we used the law of reflection to determine the location of where things were in a mirror, simple objects like a coin. Today we're going to just go and take that and extend that and look at how we could look at the location of objects that are bigger than just a single dot with ray tracing. And it's going to be a little tricky with the drawing, but you'll keep up as best you can. A reminder, you need your protractors here. I got my little family of protractors here. I believe this is the one that's going to be most useful. Again, you'll just pick on yours which one matches the size of your diagram. So we're going to be starting with something like this, and then we're going to figure out where the location of the image is of an object that's placed in front of a mirror like this. And this is basically what we're going to be doing, but I'm going to do it slowly, step by step, to trace the rays, 4 reflected rays, tracing them back and determining the location of the image of the original object. Now in optics, very often in labs, we're studying, when people do experiments with optics, they typically use candles. And so the candle is nice because it has a top of a flame and a bottom of a flame, and it allows us to see whether or not the image is upside down or reversed or whatnot. So what we do is, instead of drawing a candle, we just draw a simple arrow, because this shows us the top of the arrow and the bottom of the arrow, and we're going to see what the image looks like inside the mirror after we trace our rays. So let us begin. The first thing we do is we want to find the location of the image of where the image of the arrowhead is. So just like yesterday with the coin, we're going to pick 2 arbitrary rays. So one ray, I can just take it like this. People say, well, what kind of ray? How should I send it? Just take any ray and just make it hit the mirror like that. You could have gone like this, that's fine, or like this. Just make it start at the arrowhead and go and hit the mirror. Now what I'm going to do is I'm going to apply the law of reflection to that ray, which hit right there. And so I line my protractor up best I can, and I make a mark for the normal. And then I count out the degrees, 10, 15, looks to me like it's about 17 degrees. So I'm going to go 10, 15, and then 17 will be somewhere around here. That's the mark for the reflected ray. So now I remove the protractor, and I'm going to make a dotted line for the normal. And then I'm going to make a reflected ray go like this. So I'll put a little pause in the video. You go ahead and construct your own ray and reflect it at whatever angle that it's supposed to reflect at. Alright, now that you have that done, we'll make another ray. We could go like this, we could go like that. I'm going to go this way a little bit. Okay, so like this, and hit the mirror there. Okay. And then I'm going to reflect that. Oh, you know what I forgot? I was going to do this with colors. So let me just trace this over with the color. And that'll help us later keep track of what ray is what. Okay, so here. Okay. So I align my protractor carefully right here, the point of the protractor where the ray hits, and then this side aligned with the mirror. And then what I'm going to do is make a mark for the normal, and then count out, looks like about 11 degrees, 10, 11, so I'm going to go 10, 11 right around here. Okay, so let me construct my normal. And my reflected ray, I guess I might as well stay consistent and start with pencil and then trace over. Okay. Okay. Now, those rays reflect off the mirror from this arrowhead. They go out and spread out like this. Maybe one goes into my left eye, the other one goes into my right eye. Then my brain, as I mentioned in yesterday's lesson, will see an image of this arrowhead wherever these two lines converge or meet. So I will extend these back as dotted lines because, again, this is happening in my brain. Okay, and then I'll extend this one back. And right where they meet is where my mind sees the image of the arrowhead. So I'll write that image of the head. Where's the image of the bottom of the arrow? I have to repeat this whole process. So I again pick two arbitrary rays. One, I'll pick like this. Again, what angle? Whatever you want, as long as it starts at this back of the arrow right there. So I will now go with the green. Hits the mirror, okay? I have to reflect that ray because that's what a mirror does. It reflects the rays. So I get my protractor. I put this at the point of impact, the center of the protractor, and then line up the bottom with the mirror. That looks pretty good right there. Okay, now I make a mark for the normal. The 90-degree mark is the normal. This is actually 0 degrees, not 90, 0, the normal. And I go over and I see that this is around 11 degrees to this side of the normal. So the reflected ray, according to law of reflection, will go 11 degrees to the other side of the normal. So right about there is 11 degrees. So now I'll take my protractor away. I will construct my normal. And then I will construct my reflected ray. Okay. And I'll put a little pause in the video here for you to construct that ray. Okay, so next we need a second ray to come off the back of the arrow. So what I'm going to do is I will have a ray come this way. What angle? Well, it doesn't matter as long as it hits the mirror some angle this way. So there we go. A little bit off, but so there it hit the mirror. Now I have to reflect that off the mirror. So I put my protractor here, line it up with the point of impact, and then line up the bottom with the mirror itself. Looks like somewhere around there, okay? Maybe a little bit lower. Okay. Just try and be as precise as you can. So I make a mark for the normal, there. And then I count over the degrees. Looks like it's about 10, I'm seeing about 14 degrees. So I'm going to go 10, there's 15, so a little bit beyond that, 14. There, theta incident, 14 degrees, theta reflected, 14 degrees. I move the protractor away, I construct my normal. Okay, and then I construct my reflected ray. There. So again, these rays began at the bottom of the arrow. They spread out, hit the mirror, and continue to spread out. We call that diverging. They're diverging. This enters one eye, this enters the other. Where does our brain see the back of this arrow? Wherever these two lines converge behind the mirror. So that's what we got to do. We got to take not this ray, not that one, but the reflected ray right here and extend that behind the mirror. And same with this line here. It bounced off the mirror, we extend it. Okay, oops. There. Got a little bit away from the ruler. Where they intersect, that's the place our brain sees the back of this arrow. The light rays came like this, bounce, and then we converge them back and meet them right there. So this is the image of tail. The tail of the arrow, the back of it. The rest of the arrow we can fill in just by taking a ruler and connecting the head and the back. And not bad. Okay, so there is, so pause of the video and I'll let you catch up. Okay, so this has some patterns, and it's good to make a note of the patterns because this takes a long time and it's very tedious to find out where the image of an object is inside of a mirror. So what we can do is just make a note of the patterns so that in the future we could use the notes and draw the image without the ray tracing. And that's what we're going to move on to next. Okay, so here are the characteristics of the image. The first thing, the image is virtual, it's not real. So you know virtual reality, you know that term. That's when you put some glasses on that make a world, an artificial world in front of you. You may be reaching your hand out because it's a scuba diving virtual reality and you think there's a fish floating in front of you, but your hand is waving in the air, right? There's nothing there. It's virtual. It's inside your mind. So that's what we mean. The same thing. There's not really truly another arrow in the mirror. It's only in your mind a virtual reality of that arrow behind the mirror. A real image, on the other hand, is able to be projected onto a screen like a movie when you go to a movie theater. Or when you take a picture with your camera, the lens focuses an image of what you're looking at right onto the film. The image is also right side up, not inverted. The head of the arrow is on the top. Notice the image is reversed though. Here it's leaning to the right. Here it's leaning to the left. So the image is reverse. If you have words that you hold up in front of a mirror, the words will be backwards. All the letters and words will be backwards. Things get flipped left to right. Another point, the image, oops, I made a mistake here. Image distance behind mirror, oh, that I think is the same. Image is the same distance behind the mirror as the object is in front of the mirror. If I measure this, I would find that out to be the case. So I have about 3.2 centimeters, and that should be about the same. Yeah, it's pretty close, 3.3 or 3. Yeah, so I'm almost on. So whatever image you're standing in front of a mirror, your mirror image will be the same image distance behind the mirror. So we can write that mathematically as the distance of the image is the distance of the object. The image is the same size as the object. So if I measure the height of this or the length of this, I get the same size. And also there's a term that quantifies that. It's called magnification. So if the image is the same size, the magnification is the height of the image over the height of the object, which is exactly 1.0. And that tells me I got the same size over here. Magnification can be less than 1. If it's 0.5, that means the image is half the size. If magnification is 2.0, that means the image came out bigger. That's what happens in a movie theater. You have a little film and the light goes through it, and then it hits the screen, and then it's like 50 feet across or something like that. So greater than 1 magnification. Magnification could also be negative, and that means the image is upside down. And also that 0.5 means it's half the size. But with plane mirrors, not true. Plane mirrors, as you know, which means flat, like a plane, you always get an exact replica, same height, same distance behind, but reversed. Okay? So knowing those things, we can locate the image of objects much more quickly. I have a couple examples here. So in the first example, I put the letter L in front of a mirror. Rather than do ray tracing with all those rays, all that tedious business with protractors, no, what I could do is I could label 3 points, A, B, and C. And then just use a ruler. A is 2.2 centimeters in front of the mirror, so it gets reflected 2.2 centimeters behind the mirror. And I label that A prime, A and A prime. B, the angle of the letter L, is about 2.2 centimeters also behind the mirror. So I go 2.2 centimeters in front of the mirror, so I go 2.2 centimeters behind the mirror, and I label that B prime. C, the little foot of the letter L, is about, I'm seeing about 1.2 centimeters from the mirror. Okay, so that means that C prime, the image of that is reflected 1.2 centimeters behind the mirror. And then I have these 3 dots, A, B prime, A prime, B prime, C prime, and I realize that the letter is A to B to C, so I go A to B to C, and there's the image. So it's a quicker way rather than all that ray tracing business. You see it's right side up and reversed. If I had a triangle like this, then I would label 3 points, A, B, C. I'd measure A, okay, that's about 2.3 centimeters, so I go 2.3 centimeters behind and I make A prime. Then I see B in front of the mirror, it's about 3.4 centimeters, so I go and make its reflection 3.4 behind. Okay. C is about 1.5 centimeters in front of the mirror, so I make its reflection 1.5 centimeters behind the mirror. And once I have those 3 points located, I just connect them and make my triangle the image. Again, right side up, but reversed when it's in the mirror. The homework. Okay, so people sometimes find this a little tedious, but you're going to do ray tracing here with these 4 rays. You're going to extend this in, okay, make a normal, and then get your protractor out and make a ray reflected, right? Make the mark and then reflect that ray. And then you're going to do the same over here, reflect it with a protractor, and then you're going to extend these back, and then you're going to say, okay, the arrowhead is right here, right? And then do the same thing with these 2 rays. You reflect them, and then when you trace them back, they're going to meet over here. And then you have the image of the arrow. So I did it really quick, but that's basically what you're going to do. You're going to do this whole process with these 4 rays and these 4 rays. Then you're going to turn over the worksheet for today in the Google Stream. And then you're going to do something more like this. You're just going to reflect these points, and you could do it by eyeball. You don't have to, get your ruler out, but you could kind of go eyeball it in like that, and then connect them, and you got your image there. Okay? And do that for all these, and it shouldn't take you that long, just a couple minutes. All right, so that's today's information, and I will see you in the next video lesson.